Hello everyone, we are from Third BTech Mechanical Department in Gokaraju Rangaraju Institute of Engineering and Technology. Today we are going to demonstrate the thermal conductivity of insulating material. Objective: to determine the thermal conductivity of an insulating material at different heat inputs. This is the experimental setup to determine the thermal conductivity. Introduction: materials that offer high resistance to the flow of heat are called heat insulators. Heat insulators find extensive application in systems where heat losses are to be minimized, such as heat transmission line in power plants, furnaces, etc. Insulators have low quotient of thermal conductivities, about 0.1 to 1 watt per meter degree centigrade. This setup has been designed to study conduction heat transfer through insulating material and to determine its quotient of thermal conductivity. It is well known that rate of heat transfer to a material is given by Q is equal to K into A into delta T by delta X, where Q is the heat transfer rate in watts and K is the quotient of thermal conductivity watts per meter degree centigrade. A is the surface area of the heat flow. Delta T is the temperature difference between the walls in degrees centigrade, and delta X is the thickness of the material in meters. Coming to the apparatus of the experimental setup, insulating sphere. Insulating sphere, it consists of two concentric spheres of 1.5 mm wall thickness. The inner and outer surfaces have 200 mm and 250 mm diameters respectively. The space between the spheres is filled with insulating material. The inner sphere is filled with oil. Heater has been installed inside the inner sphere to heat the oil to the required high temperature. The arrangement is such that heat transfer inner surface to the outer sphere through the insulating pond can be studied. Coming to the heater, it is used for heating the oil inside the inner sphere. In this setup, the capacity of the heater is 400 watts. The heater switch is used for on and off. And voltmeter, it is used for measuring the potential difference between the 2 points in the electronic circuit. Ammeter is used for measuring the current in the circuit. The voltage and the current are used for determining the power in the calculations. Temperature selector is used for indicating the temperatures at the different locations of the sphere. Thermocouples. Thermocouples are used for sensing the temperatures at different locations. In this setup, we are using the K type of thermocouple. In the sphere, temperature points at where the thermocouples are located are 1, 2, 3 thermocouples are at upper hemisphere and the 4, 5, 6 thermocouples are at lower hemisphere, and the seventh thermocouple is placed at the oil. Thermostat. Thermostat is used to set and control heat temperature. It ranges from 0 to 150 degrees centigrade in this setup. And the mains is used for passing the AC current from the main source to the setup. Heat control. Heat control plays an major role in the experiment because of it is the regulating heat input to the.
In the determination of the thermal conductivity of an insulating material, the next step to be followed is the working principle. In the working principle, the schematic diagram of the heat transfer process through the insulating sphere is shown. This consists of the two surfaces, inside and outside surfaces, on which the different thermocouples are mounted to find the temperatures inside and outside the surface. Into this, a heater is connected, which is penetrated into the surfaces, and the electrical energy is supplied so that it converts into heat energy, and the temperatures are obtained in the digital temperature indicator. And this determination of thermal conductivity of an insulating material follows Fourier's law of heat conduction formula. Fourier's law of heat conduction law, which is given by the equation Q equal to Ka dt by dx. Q is the heat transfer, A is the surface area of heat flow, K is the thermal conductivity of insulating material, and then the interesting term used here is the shape factor. It is an important factor which is given by the equation 4 pi r naught ri by r naught minus ri, where r naught is outside radius of the sphere, that is 0.125 meters, ri is the inside radius of the sphere, that is 0.1 meters, which can be substituted in the shape factor equation so that we get that is the 6.28 meters in the present setup that is used. Here the shape, it is a fraction of the radiation energy that is diffused from one surface element and strikes the other surface directly with no intervening reflections. The other names of this shape factor is view factor, angle factor, and the configuration factor. Here the important thing to follow is to find out the temperature difference, that is the Ti minus T naught, that is delta T. Ti is equal to T7. Here we will be finding the temperatures from T1 to T7, that is Ti is the summation of temperatures, Ti is the T7, T naught is the summation of temperatures from T1 to T6, that is the average. Then the next step to be followed is the operational procedure. In the operational procedure, the first and foremost step is to switch on the mains, then the console and the heater. Then the next step is to switch on the thermostat and set the temperature indicating, say the required value may be less than 150 degrees centigrade. It should never exceed 150 degrees centigrade. Then set the heater control or the dimmer stat and set the input power to the heater, maybe like 100 watts. Then wait for a few minutes, maybe 10 minutes, till the temperatures are constant, that is the steady state is obtained. Here the steady state is whatever the number of times the experiment may be done, the set of readings, the values that are obtained are constant, that is under the steady state. It is a steady state. Then read the temperatures from T1 to T7 using channel selector and the temperature indicator. Then read the input power to the heater from the wattmeter. Then using the measured calculations, we can find the coefficient of thermal conductivity of the insulating material. Then the next step is we need to note down all the readings in the observation table, which consists of the power, that is the product of voltage and current, and then the temperatures from T1 to T7. T7 is the inside temperature and outside temperatures can be calculated from the summation of T1 to T6, that is the average. Then the two readings that are shown in the following observation table is that which are obtained in the laboratory, that means that which we have undergone. From these following readings, we can easily find the thermal conductivity of an insulating material using the Fourier's law equation, that is Q equal to Ka dt by dx.
Coming to calculations, the coefficient of thermal conductivity K is given by Q by R delta T. Here Q is power input, and R is a shape factor, and delta T is change in temperature. R shape factor, we should consider here shape factor because it is not a cylinder, it is a sphere. There will be a change in diameter at every cross section when we go into the when you see in the axial direction. And then delta T is given by T1 minus TO. Here TO is the average of all temperatures, all the first 6 temperatures, and Ti is the initial inside oil temperature. Then is the inside oil temperature of the sphere, and this is the average of the all temperatures, and it is calculated as the outside temperature of the sphere. Delta T is given by inside temperature minus outside temperature. R, the shape factor, is given by 4 pi radius into outside radius into inside radius divided by outside radius minus inside radius, and here the shape factor is 6.28 meters. Q, for the first calculation, the Q is 43 into 0.1. Here the 43 watts and 0.1 amp, 43 volts and 0.1 amperes. It is 4.3 watts. And delta T is temperature inlet minus temperature outlet, which here is 14.32 degrees centigrade. The coefficient of thermal conductivity K is equals to the power, which is 4.3 watts, divided by shape factor 6.28 into change in temperature 14.32. And the answer, thermal conductivity of the insulating material K is equals to 0.0478 watt per meter degree centigrade. The table of results is given like that. Initially we have to write the power input, and then the temperature outlet, outside temperature, inside temperature, and the change in temperature, and the coefficient of thermal conductivity of insulating material. Precautions: we should use a stabilized power supply, and we should not give directly a large amount of heat supply power input. If the temperature is directly drastically increased, and there may be a effect that the insulating material inside the sphere may damage. Keep the dimmer to start 0 before starting the experiment. Use selector switch knob and dimmer knob gently so that they may damage. Thus the thermal conductivity of insulating powder at various heat inputs has been determined.